Okay, this is lecture 11, part A. We're going to talk about something called the population games, and this part A is going to provide you some motivation about why and why do we need the population games, why it is useful, and what actually the population is. I'm going to talk about more general stories in the next lecture. But probably I'm going to give you the two examples to motivate the population games, and then probably you will find why this can be useful. And the example is that well, we're gonna draw on a different interpretation of the symmetric form game. It's the same thing, but different interpretation. And also we're gonna talk about something called the non-atomic congestion game. So the congestion game has been discussed in the section of I guess potential game, but we're gonna look at a different version of that, and that can belong to one example of the population game. And as I mentioned before, again, the population game generalization will talk about in the next part, like 11b. Okay, all right. Just as an aside, the population game is also called something called the evolutionary game. If you type the Google this with this keyword like evolutionary game and the population games are more or less these are highly related. I mean the definition is a little bit different, but whenever we talk about the evolutionary game, that it actually is one of the population games. Okay. The reason why we use the evolutionary game is that this population game has been developed from I mean, this has been studied by the starting the discussion from the biology. Like they wanna discuss how uh, the animals or the lives evolve, where we have some fitness issues and the mutation issues and so on. Okay, we're gonna talk about it later. Okay. Okay, this is a first example. This is the game which is called the hawk and dove game. If you probably some of you remember what the hawk and dove game, but let me remind you about what this game is. And suppose that there is a resource with the value v, and that it should be shared by the player 1 and player 2. Okay, and if a player plays hawk, okay, we have two strategy: hawk and dove, and hawk and dove. Hawk is like animals who is very aggressive, right? And dove is like animal which is non-aggressive. So if a player chooses a hawk strategy or plays hawk, it is aggressive and will try to take the whole resource for itself because it's aggressive. And if the player is playing dove, I mean dove is pretty less aggressive than hawk. So it's their strategy is more like very non-wild in some sense. So if both players play hawk and they're very aggressive, and they share the resource V, but they lose something because they're too aggressive. So like they lose like c over 2 is the amount of that they lose when both of the players choose hawk strategy because they are too wild, too aggressive. I mean, think about the sort of the fight between two like male lions. Okay, in order to mate with the one female lion, I mean they need to fight, and they sometimes scratch their faces, each other lions' faces, and so on. Right? They lose something. But if they choose both of the players choose dove, I mean dove is pretty non-wild, non-aggressive. That so they shared without any loss, and that's why the payoff is v over 2 and v over 2. But if the player 1 is playing hawk and the other player plays dove, and obviously dove is too non-wild. So the hawk strategy player will dominate the resource. That's why the player 1's payoff is B, but the player 2's payoff is 0, and the other way around. Okay? So that's a hawk and dove game. So I guess everybody understands this thing. And we can actually interpret this payoff structure as as corresponding to some notion of the fitness. I mean, we know what the fitness means in from biology, right? It's basically the greater consumption of the resources leads to the more offspring, meaning that, well, if for example an animal and another is an animal, and animal is pretty much release. Animals are interested in generating or the producing more offspring or more children. That's their instinct, right? And the resource sharing mechanism can correspond to, I want to have a better fitness to the nature, meaning that by having more resources, then I can have more power of producing more offspring. And if we can understand this hawk and dove game as a what's happening in the society of the animals, it's pretty much this problem is motivated by the evolution of animals or the lives in our world, and that's why this game has been thought by the biologist. Okay, right? Okay. So good. I'm just connecting this hawk and dove game to the fitness concept in biology. So let's understand this game from a perspective. I mean, this is just a normal form game, right? It's a normal form game. We know that. And there are some issues of the pure strategy and pure strategy, mixed strategy, everything that we can talk about as we learn in the second and third lecture. But we're gonna provide a different interpretation of this game. So these are the different interpretation. So we will look at this game from the following perspective. Suppose that we have a large number of populations, which means that there are sort of infinitely many people or the animal here in this population. Okay, and I call this is an entire population. So entire population is divided into the following two portions depending on their strategy choices. For example, suppose that let's say like this distribution. If we normalize this entire populations where the number of animals in this population is almost infinite, but we normalize by 1, then we can think about this portion of xh and xd, where the xh portion of the population chooses the strategy hawk, and xd portion of the entire population is choosing dove. Okay, all right. So I'm going to look at this game as I have to explain this first and this thing. Yeah, I made a mistake of the switching the slides. Okay, yeah. So here, okay, here the society large number of population of a society. Okay, and this society consists, as I mentioned before, consisting of the many humans or the animals, if you like. who wants to have more want to have a more offspring. So in order to have more offspring, they need to share larger resource. I mean, that's the sort of the game that we're looking at in this hawk and dove game. Okay, so since there are infinitely many animals, individuals in this society, and each infinitesimal human, infinitesimal means that it's so small that we can ignore the each individual. It's a very small point. So each human is infinitesimally small, and this human is we're gonna assume that we're gonna interpret this game as the game where each human or animal is matched to play this game, where each pair of humans meet exactly once. So we are, which means that these are the humans or the animals. Okay, and we will look at we're gonna consider the situation. Each infinitesimal individual will play this game with another person exactly once. Like the game between these two guys, game between these two guys, game between these two guys, game these two guys, and so on. We're gonna assume that there are many infinitesimal and infinitely many individuals. Okay. Now we're gonna consider the let's divide this population where some portion of the population, like xh portion, and this is an xd portion. If we normalize the entire population, then we can easily assume that the xd and xh are between 0 and 1, right? If we normalize by the entire population by 1, okay, here. Okay. So xh people, xh portion of the people chooses hawk strategy, and xd portion of the people choose this dove strategy, and then they meet exactly once and they play this game. Let's consider that situation. All right. Okay. Then like here, as I mentioned before, then what is the average payoff of choosing strategy hawk for a particular person, for a particular individual? What is the average payoff of strategy choosing hawk? So here, forget about this player 1 and player 2. Okay, and then I'm choosing hawk, but I can meet a lot of people here, even hawk. So here I'm I, this is I, this is me, and as I mentioned before, I'm going to match with the guy here or here and play this game. So then the portion that I'm playing the game where my opponent plays hawk is xh. Why? Because xh is the portion of the entire people which chooses hawk, and the portion of the opponents that plays is the dove is xd. Okay, I normalize that. Alright, then what is the kind of average payoff of choosing the strategy of the playing hawk? That is the xh multiplied by e1 over 2 v minus c plus xd v. Is that right? Oh, probably. Well, you can interpret this game as, okay, entire population is n, and xh is the portion of the people that chooses hawk. Then we can just normalize like by n, where the n goes to infinity. I mean, if we normalize that, this that's what I mean by average, right? What is the average payoff of choosing strategy dove? Well, when I choose dove, then average payoff would be the portion xh multiplied by 0 plus xd and 1 over 2. Right? So if I'm the guy here, under the condition of this, under the condition that every population is dividing the following portion of depending on their strategy choices, then I can compute the average payoff using this way. Using this way and that way. And if we move our perspective to not me, but you are here, but you are infinitesimally small. And that's why we can compute the expected payoff in this way. And we can do the same thing. Alright? And probably we can understand how the animals and the humans behave in the jungle. Where, well, how many people are choosing the hawk strategy, how many people are choosing the XD strategy, and so on. So fine. So given a normal form game, we can interpret this normal form game in a different way, and that's exactly what I'm doing. I'm just interpreting this game in a different way. Alright? And now look at what happens. Now look at what happens. Well, this XH and XD is the portion of the entire population that chooses hawk strategy and dove. And it's a similar thing, right? This is not the player 1 and player 2 anymore. This is what happens. Right? Well, look at it. I mean, well, this is exactly what happened where if the player 1 and player 2 uses the mixed strategy XN, XH and XD and XH and XD, like player 1 and player 2 in the normal form game, then XH and XD can be regarded as a mixed strategy profile in a normal win game. But I have a different interpretation about what's happening to the animals and life in the society. So the mixed strategy choice XH and XD can be regarded as the strategy distribution. Of the population. Right? What is XH? XH is the number of people or the portion of the people out of the entire population that chooses hawk strategy. So so if you will look at this normal form game from the different perspective, where the different perspective is called the population game, a strategy is nothing but a vector of portions of the humans X, H, and D, where each portion corresponds to each strategy. Which means that in the normal form game, a person's choice of some strategy S, whatever, like hawk and dove, or their combination of probabilistic combination, which is a mixed strategy profile, is nothing but a portion of a people which chooses strategy A, S. In my different interpretation. So this world is called the population game. And this world is just normal form game. I'm just starting from the normal form game that we have learned, whether it is a pure strategy profile and the mixed strategy profile. I have a different perspective of interpretation of one mixed strategy profile in a different context. Means that I'm going to define this world as a population game. Again, as I mentioned before, we're going to look at more general interpretations or general formulation of the population game. But as you see, that's, well, the reason why we use the word population is that essentially we're gonna consider the each player as a very infinitesimally small player, which means that it does not make any impact on the payoff changes. All the kind of structure or the dynamics or the picture that I'm looking at is kind of a macroscopic behavior. We have an entire world, and then there's some portion of the people which uses a different strategy, and this portion can be regarded as a mixed strategy profile in a normal fun game. In the population game, that corresponds to the portion of the people which uses the some specific strategy. Portion of the people. And that's pretty interesting, right? So I hope that you have a sense of what's happening here. I'm just starting from the normal fun game, and I have a different interpretation. From the perspective or from the assumption or from the angle that's entire world, there's an entire world like society, and there are lots of many populations, and then there are some different distributions of the population which chooses different strategy like XH and XD, and then we assume that game. So the strategy here in the normal form game is just the probabilistic distribution of the strategies, but here it's the same thing, its outlook is same thing, but the interpretation is different, like a portion of the people which chooses a strategy. Here the main assumption or the main angle that we have this kind of interpretation is that we're going to consider the large number of populations. Alright? Let's look at a different example. Well, the different example is that congestion game. So do you remember what the congestion game is? This was the original congestion game that we have looked at in the potential game lecture. For example, in this picture we have three players, A and B and C, and this like A slash B slash B C means that it's a cost when one or two or three players use that road. So like A and B and C are independently choose their path to the terminal. Like for example, A chooses this thing, and B chooses this thing, and probably C chooses this thing. And then the cost that we will experience over this link is, since we have two people, this is 3, and this is 1, and this is 1, and this is 1, and this is 1. And obviously they have a lot of choices, which means that's a path. And this is a game because A's strategic choice will make an impact on the B's payoff, because the B's payoff is determined by the link cost or the congestion cost. So the total cost of each player is the aggregate link cost over each path, right? That's what we have looked at. Yeah, we know this congestion game, and we proved that this congestion game is a potential game. That's which is good. But we will interpret this game in a differently. I mean, not differently. So by summarizing this the game congestion game, which I call it earlier model, but I'm going to use a different model which is very similar to the earlier one, but it has a different interpretations or a different form of the game. So this is the game that we have looked at. Okay, I used the different notations in the potential game lecture notes, but I just copied some lecture material, so we use a different terminology where E is a set of finite congestion elements. Here in this case, links. Okay, it's a link, and we have a players, n players, each with a strategy set as I, where each strategy is essentially a subset of E, or you can say it's a path. Okay, I have a lot of path, so this is a set of all path, from S to D. Okay, and there's a cost function which we call the delay function of some particular link, and that cost function is probably the function of how many people are traversing that link E. Right, so if we have more people, then the cost function, delay function will increase. So for the given a strategy choice is pi of the player I, which is a path, and the congestion on each element E, element is a link, given by xe. Xe is what? Xe is a number of players using link E. Okay, and delay on each element is given by de, some function which may depend on the link of and the number of people who are using this link. And the cost for the entire each player I is the summation of its path or strategy, the cost or the delay. And that's what we have looked at in the earlier case, right? I'm just give you the reminder of our earlier game. So I guess everybody's clear about that. Now we're going to look at a different perspective. We're going to define a very similar to the earlier congestion game, but in a different way. Now we will assume that there are three classes or the types, not the three players, from S to T. Three classes. These are something called the classes, not players. So I'm going to provide a different interpretation. I'm going to define a different game, different congestion game, which is similar to the earlier game, but it's different. Now each class can be regarded as a player here in this case, but it's not an individual person which chooses the path, which is just class. So the multiple classes are playing the game. These are the class. Okay. Now suppose that each class has its mass. Mass may be, so like class A can be regarded as a population of infinitesimally small individuals. You can regard it class as the population of infinitely small individuals. Like class A is what? Like some people, like some senior people. Like class B is some junior people, and some class C is some like a collection of the babies. But it has a different mass. Mass means that what's the size of the population. Okay. So here in this case, you can regard this mass with the rate of the traffic that needs to be delivered by the class I. I mean, if you think this is a road, then the class A is probably the collection of the cars from Samsung company, and B is a class of the cars from the Hyundai company, and things like that. And we're gonna use the word mass. And from the perspective of the traffic, and this can be regarded as the amount of the traffic that needs to be transferred per unit time, or you can define as the rate of the traffic. I mean, for the meantime, you can regard the RA is equal to 1. It has a unit mass. Now each class select a strategy from the strategy set SI. Still here in the SI is what? A set of path, right? Right? Of class I. Now each class of the players, where each class is a player, each class of the players is allowed to distribute fractionally over the strategy sets. Like for example, like from class A, then there are lots of paths, but like this is one path, and this is another path, and this is another path. Okay. Now if we distribute like X, this is a distribution of XA, but the first distribution, and this distribution of the class A, the second distribution, and the third distribution. Now what is XAJ? That's the portion of population A that chooses the strategy I. Is that right? And we can similarly define xp1, xp2, xp3. That's the portion of the population B, or class. Here I'm using the class type population, same thing, that chooses the strategy I. The same thing for the xc1 and xc2. Okay? Can you see the similar things from here to here? I guess so. Here the strategy is what? Strategy is, for example, like population, or the class A's strategy is a distribution of the traffic This is one strategy. This is the strategy of class A, right? And we can have a strategy of class B and C and so on. It's exactly the same thing, where because well, this if we normalize by this math, or suppose that the math is 1, then this is nothing but a mixed strategy profile. Mixed strategy of player A, or type A. Here the player is type, and the strategy is what? It's what? Distribution of the traffic. Here the player is what? Player is entire population, where what is the strategy? That's the portion of the distribution, or distribution of the entire population that chooses H and D. The same thing. I'm providing a different interpretation of the congestion game, or not different interpretation. I'm defining a different game essentially, which is similar to the previous game, but here is it's different. Now, what's the difference between this this congestion game and this game? We're in the Hawkdove game about this population game level interpretation. Here there's only one class, right? Because I'm only considering only one society. And then we think about different distribution of the people, or the portion of the people, which uses a different strategy. But here I have 3 classes. That's the difference. But essentially the remaining thing is same. So if you remove the A and B, then this game is almost similar to this guy. But I mean, the situation that I'm generating the game is a little bit different. So the difference between two games means that the original, the congestion game, and this population based congestion game is that, well, in the first game we do not allow a splitting of the traffic, and that's why we call it this is an atomic congestion game. Okay, where we have a finite number of users, where each user can take a path from a discrete set of the strategies. But here in the second game here, we consider the player as an entire class, where we regard the entire class is the collection of infinitesimally small population or person, and then we allow the splitting of the traffic, where the splitting means that we essentially allow each small individuals to be splitted over the different path. And that's why this is splittable congestion game, or the non-atomic game, where we treat the traffic similar to the flow in a network, where we can split up the load to the several paths. And analogously, we can look it as infinitely many users, where each user controls the infinitesimally small portion of the total traffic. Now you probably see the difference between this population game. What is a population game? So in a population game, I'm going to look at more general stories, but well, essentially we consider the population or the society, where we can regard each individual person as a very, very small person which just forms a society. So here in this case, what is a strategy? I mean, we cannot talk about the strategy of an individual. We need to talk about the portion of the population that chooses a specific strategy. So particular portion of population, and that can be regarded as a strategy. If you allow now the general portion, then these can correspond to the mixed strategy in a normal fin game. So the reason why we are considering this population game is that it provides a different angle to look at the system, look at the world. And we can have a multiple society in general and different path, and even there do the gaming. I'm going to talk about the more general stories. Now, I'm going to conclude this lecture by mentioning why this was first developed from the biology. Well, then the biology, for example, they want to look at the behavior where, oh, there's an entire society, and there are some like lions here. They have some mutations, for example, and they have like, for example, a collection of the like animals like lions. And they can choose a different strategy to have in order to have a more offspring. Again, like hawk and dove game, they can be aggressive, they can be dove, and there are different kinds of animals who are living in the same world, and they sort of compete with each other, and then they mutate, and then their population increases, decreases, and then we have here, and they wanna look at what happens in this animal society. And that's why they try to look at this situation as, well, there are many, many animals, or even genes. Okay? There are many animals, they are competing with each other in order to have a more offspring. And then how should we look at the game? Look at this thing. How should we model this thing? Well, there was a game theory. And then probably we can use this game theory, but we can think about this thing in a different way. Meaning that, well, we have a lot of there exists a population which consists of a lot of animals, and then sort of they choose a different strategy, and then what we are interested in is the portion of the strategy. And depending on the portion that a particular animal class chooses the strategy, like hawk and dove, for example, then obviously there is a different like equilibrium concept. What's the dynamics upon this choice of the strategies and so on? They want to try to look at that. So they are sort of looking at the society as a macroscopic behavior, where main quantity that we are interested in is the portion of the entire population that chooses a particular strategy. Okay? So I'm going to talk about the more general stories. I hope that this this motivating slide will give you just a little bit of sense of what would be the population game. I'm going to talk about the more things. So if you don't have any clear picture about this population game, I guess the next lecture will serve you the sort of those clear picture of what is the population game. Okay, so just wait for some time. Okay, thank you.